Hey guys, welcome back to another session of Proofs with Jimmy. Today we'll be proving proof 8. And in proof 8, we're going to define the Lebesgue integral and we're going to illustrate the definition of this by calculating the integral from 0 to infinity of e to the negative x dx as a Lebesgue integral. So the first thing we want to do is to define the Lebesgue integral. And we can first do that by defining it by first writing a function f of t in the context of this function here as equal to e to the negative t, such that t is between 0 and infinity. And the reason why we are writing this function in the first place is that if we think of this as a series of functions, it'll be more clear as to what we'll be doing when we're trying to define the Lebesgue integral. But for now, we're going to define this as a series of functions. And because it's a series of functions, we can then rewrite this as the sum from k equals 0 to infinity of f of k of t, such that f of k of t is defined in this piecewise function as e to the negative t, where k can, or where t can take on values between k and k plus 1 and 0 otherwise. Okay, so what is this going to look like when we actually visualize what this looks like? Well, if we draw this out on a plot here, and we have the function e to the negative t here, e to the negative t here, then this function fk, f sub k, and then I'm going to change colors, is defined between k and k plus 1 to be precisely this value of e to the negative t, but only between k and k plus 1. For all other values, it's going to take on 0. And so we'll be working with multiples of these functions defined on different definitions of k. So this is just like one instance of k, where k is defined between, or where t is defined between k and k plus 1. This is just a single instance of that. But when we take the series of these functions, that's ultimately going to give us our Lebesgue integral. And so now we're going to test for Lebesgue integrability here. So we're going to test for Lebesgue integrability. And so we're going to do that by first calculating each kth integral of each member of the series here. And so we can do that by calculating I sub k. And again, I sub k just simply means the kth integral of each member of the series. And so it's the integral from 0 to infinity of fk of t, as the value dt. And because we know that f of k is defined specifically between k and k plus 1, we can then rewrite this function as the integral from k to k plus 1 of e to the negative t, because of the way we defined it our piecewise function up here, of dt. And so what is the point of doing all this in the first place? Why are we only caring about the kth integral here? Well, we want to create a simpler like f of k that has bounded support and is a bounded function itself. And so what that means is that f of k would then just be a Riemann integrable function. So now the next step now that we have like this sort of setup here, is that we want to show that whether or not this kth integral converges. And so for the test for Lebesgue integrability itself, we want to see if this kth integral converges. So in this test, does the series of k equals 0 to infinity of I to the k actually converge? And we can actually do this using the convergence test. If we were to say that each kth integral is less than e to the negative k here. And so what does that look like visually? Well, if we have it such that we bound it by e to the negative k, then the area that's defined between k and k plus 1 would just be this area here. So now let's proceed with the comparison test itself. So for the comparison test, we can then say that comparison test, we can say that the series from k equals to 0 to infinity of e to the negative k. This can be just rewritten as the sum of k equals to 0 to infinity of 1 over e to the k. And because we know that this common factor, 1 over e, is less than 1, and we know that this whole thing here is simply just a geometric series. So geometric series. Ultimately, we know that this series converges here. So with this, now we know that the integral from k equals to 0 to infinity of the kth integral converges. And so ultimately that tells us that the Lebesgue integral exists. So now we can then talk about the Lebesgue integral itself and what we mean when we calculate its integral. So now we have the Lebesgue integral. So it's the integral from 0 to infinity of f of t dt. And then we can write this as the sum from k equals 0 to infinity of each of the kth integrals. So then this can be just so, and the kth integral is defined before as this here, except we'll be making one change. And that is that f of k of t dt, this thing doesn't have an absolute value around it. And so now that we have this, we can then rewrite this as the sum from k equals 0 to infinity of the integral of k to k plus 1. Again, because we said that based on this piecewise function, it's defined, t is defined between k and k plus 1. Otherwise, it's 0 for all other values. So then the rest of it is just e to the negative t dt. Okay. And then once we actually carry out the integration on this can be then rewritten as k is equal from the sum from k equals 0 to infinity, and then integral. So when you take the integral of this simply just becomes negative e to the negative t, defined between k and k plus 1. And then when we write this out further, what this looks like is that it's going to look the sum again of k equals 0 to infinity of e to the negative k minus e to the negative k plus 1. And then once we have we can group together the terms that we have here. And so what's that going to look like? Well, the way it's going to look like is that we can have the sum from k equals to 0 to infinity of 1 minus e to the negative 1 of e to the negative k. And then we know that there's no k term in here, so then we can then kind of take it out. So what it looks like is that it's going to be 1 minus e to the negative 1 of the sum from k equals 0 to infinity. We can also rewrite this so it's simpler. So then it would just look like 1 to the e to the k. And so we know that this converges based on the work that we've done up here. So then we know that and it converges specifically to the geometric series. So then this can then be written as 1 minus e to the negative 1 times 1 over 1 minus 1 over e here. And so based on how these work, they're basically like inverses of each other, or one is the reciprocal of the other, basically. This simply just gives us 1. And that should end the proof. But I guess to make it more clear, we can rewrite the first term. So we can write this as 1 minus 1 over e. And then this is just 1 over 1 minus 1 over e. And so it's kind of obvious now that this is now equal to 1. And that should end the proof. Thank you so much.